To understand the concept of the unbiasedness, we just take a simple example, that is example number 1. Let x1, x2 up to xn be the IID from the normal population having mean mu and variance sigma square. Let mu hat, that is x bar, and the sample mean, which is the sample mean, and the sigma hat square, that is the s square, which is the sample variance, then show that mu hat and sigma hat square are the unbiased estimator of mu and sigma square respectively. So how we proceed for this one? As we know that we have x1, x2 up to xn be the random sample of size n from the normal population with mean mu, then the x bar, that is equal to 1 over n sum xi. So we take the expected value of x bar, that is 1 over n, and then expected value of, we just open all these, x1 plus x2 plus so on up to xn. Next we apply the expectation on the every x, that is expected value of x1 plus expected value of x2 plus so on expected value of xn. And we know that the expected value of x1, that is equal to mu, so that is 1 over n into mu plus again this expected value of the x2, again it is mu, and plus up to so on, that is mu. So that is for n times, so we can write it as, that is n mu over n, and it will give you the value mu. So the expected value of x bar, that is equal to its population value. So we can say that the x bar is an unbiased estimator of mu. Similarly, for the sigma square, that is, we just use the s square here. We know that that is 1 over n minus 1 into sum xi square minus n x bar square, and we use some relation here for this one, that is, we know that it is well defined result, expected value of x square, basically that is equal to variance of x plus expected value of x whole square. And also we know that variance of x bar, that is basically equal to 1 over n variance of x. Now we take the expectation on both sides, that is the expected value of sigma square, that is equal to 1 over n minus 1 into the expected value of sum xi square minus n expected value of x bar square. So we can write it as, by using the previous facts, that this value can be written as सम है तो ये n बन जाएगा, और ये हमारे पास वेरिएंस ऑफ x आ जाएगा, जो भी हमने पीछे रिलेशनशिप यूज किया है, एक्सप्लेन किया है, उसको हम यूज कर रहे हैं, प्लस n expected value of x whole square, and on the same way for the x bar you can write it as minus n variance of x bar minus n expected value of x bar square. सेम फैक्ट हमने इसके लिए भी यूज किया है. नाउ यू कैन राइट इट एज दैट इज 1 over n minus 1 that is n variance of x, basically that is sigma square. सॉरी यहाँ हम एस स्क्वायर लिखेंगे क्योंकि हम सैंपल को एक्सपेक्टेड वैल्यू ले रहे हैं और वो हमारे पास पॉपुलेशन के बराबर हम प्रूव करने की कोशिश कर रहे हैं. सो वी राइट हियर इज द एस स्क्वायर विच रिप्रेजेंट द सैंपल वेरिएंस. सिमिलरली प्लस एन expected value of x जो है, we know that is the mu, so we can write it as mu square minus n into variance of x bar. We have already given this fact that is 1 over n, and that is variance 1 over n into sigma square आ जाएगा. Variance of x होगा which is sigma square and minus n mu square, this one. So further you can see that कि ये हमारे पास n mu square के साथ कैंसिल आउट हो जाएंगे, ये n इसके साथ कैंसिल आउट हो जाएगा. Then we have that is 1 over n minus 1 into n sigma square minus sigma square. So that is basically 1 over n minus 1 into sigma square. आप कॉमन लेंगे तो that is n minus 1 and this will cancel out. So expected value of s square, that is sigma square. So we can see that the sample mean, we have already proved that the expected value of x bar, that is equal to mu, and the sample variance is equal to the population variance. So we can say that the sample mean and the sample variance are unbiased estimator of the population mean and the population variance in the normal case.